So what this means is that this is just the Lorentz transformations in the x direction, right? There are other embeddings. So for example, if I have, so the lambda matrices, as you know, can be expressed in terms of, lambda will have the form of, say, cosh zeta, sinh zeta, and cosh zeta, right? So there are going to be many embeddings of this group inside this group, and corresponding to boosts along x, y, and z direction, right? So there could be, say, boosts along x, y, and z direction. Now, since SO1,1 is a non-compact group, and since I can embed it in SO1,3, it follows that SO1,3 is also a non-compact group. Right? You cannot hide something of infinite volume in something which is finite volume unless you're Doctor Who. Even the inside of the TARDIS is not infinite. It's huge. It's bigger on the inside, but it's not infinite. Okay, is that clear? Do you have any questions about this? Okay. Hello?
Yes, sir.
Can someone?
Hear you.
Sorry?
We can hear you, sir.
Okay, are there any questions about this?
No, sir.
Okay, so the idea, the thing is that, SO1,1 is just a real line, which is a pretty simple geometry. Can someone tell me what is the dimension of SO1,3? What about SO4?
Four.
Okay.
Oh.
So there are going to be here, let's think physically. Here, this is the Lorentz group, so there are going to be 3 boosts. There are going to be 3 rotations. So you're going to have 6 parameters.
Sir, what are we talking about when it comes to boosts? Like, what is it?
Oh, in special relativity, if you have, say, a frame of reference, say S, and if you have another frame of reference, say S prime, sorry, let me make sure there's no prime here, S prime, which has X prime, Y prime, Z prime, and suppose S prime is moving with some velocity, say V, within the S reference frame. So then we say that S prime is boosted by the velocity V. Now suppose that the boost is such that V is in the X direction, in the Y direction, well, let's call it x direction just for simplicity. Suppose this is my the velocity, then suppose we have some point here, some physical event. So this is some event or some physical point. No, let's take an event. So this event will have some coordinates in both reference frames, right? So then the time coordinate and the x coordinate of this point, and there's going to be, of course, the other, so there's t prime, x prime, y prime, z prime, right? These are the coordinates of the, let's call this point P. Okay, these are the coordinate of the point P. So this is in reference frame S prime. So they're going to have this point is also going to have x, t, x, y, and z coordinates in reference S. So Einstein discovered that these are related by a transformation which is linear. And the linear transformation for this particular one will have the form of cosh of zeta.
Oh, I think I got it. Yeah. Now I
Inch of zeta. Yeah. Let me just finish this anyway. Okay, so these are the Lorentz boosts. They're called the Lorentz boost, where zeta is, I think it's tan hyperbolic of zeta is, say, v. Okay?
Yes, sir.
Okay. All right, so, okay, what about SO4? So SO4 consists of 4x4 matrices which satisfy this condition. If I write this as in terms of indices, it's a matrix multiplication OIJ, OJK is equal to delta IK. And there's an implicit sum over J, which I'm not going to write. Right? So this is an equation. So O has 16 entries, right? 16 entries, but this is a symmetric equation, right? Because INJ is symmetric. So here we have how many equations? Independent equations. When I is equals to K, we have 4 equations, right? When I is not equals to K, we have 12 equations, but because of the symmetry, we have 6 independent equations. So we get 10 conditions. So the number of independent parameters is 16 minus 10, 6. And this counting does not change whether we are dealing with SO4 or whether we are dealing with SO1, 3. In the case of SO1, 3, this equation just changes by this equation, right? And this equation is the same number of components as this equation. Okay, now here, is that clear? So another way of you can think of why SO3, SO4 has 6 dimension is the following. You can think of SO4 as the rotations in a 4-dimensional Euclidean space, right? So in 4-dimensional Euclidean space, you've got 4 directions. So what are the independent rotations? 1, 2, 1, 3, 1, 4. 2, 3, sorry, because 2, 1 is taken and 2, 2 is not a plane. So 2, 3, 2, 4. And then we have 3, 4. These are the independent planes of rotations in 4-dimensional space, 4-dimensional Euclidean space, right? And therefore, SO4 has 6 dimension. In the case of special relativity, we can think of time as the 0th dimension. So we have rotation, quote unquote rotation in 0, 1 direction, 0, 2 directions, 0, 3 directions. These are imaginary rotations, so that what used to be sine becomes sinh, and what used to be cos becomes cosh. Okay, so these are the boosts, can be thought of as some sort of imaginary rotation. And then we have the usual rotation between 1, 2, 1, 3, and 2, 3. So this is SO, this is SO1, 3. Okay, so we can actually go from SO4 to SO1, 3 by doing the analytic continuation. Okay, where basically what happens is that what used to be, say, the 4th direction here becomes the 0th direction. So what used to be x4 becomes I of x4, and we call it t, or x0 over here. Okay, this is known as Wick rotation, and it is something that is very useful in quantum field theory. But does this make clear up the counting a little bit? Are there any questions about this chart? Nahi, I think you are the one who said the dimension of SO4 should be 4. So can you tell me if this is clear data?
Yes, sir.
Sorry?
Yes, sir.
Okay, good. Okay, so yeah, these are kind of, with a lot of, with exposure, you will get used to these facts. This is nothing very deep. Okay, so let's carry on. Oh, I think we are almost at the 6 o'clock mark, so let's take a 15-minute break, and let's meet back here at 6:15, okay?